Thank you for taking the time to listen to a brief introduction about the Nautilus software. I'm Suhas Kulkarni. I'm the founder and president of FimmTech that I started in 2004. I have a master's in plastics engineering from UMass Lowell. I've got experience in injection molding since 1993. I'm also the author of the best-selling book, Robust Process Development and Scientific Molding by Hansa Publications. So what does the software do? There are 5 elements that are very important to achieve the quality of a molded product: the part design, the material, the mold design and the build, the choice of the molding machine, and the molding process. The Nautilus software, it helps in machine selection, it helps you to evaluate and establish the molding process. It also helps you in process transfer, documentation, machine validation studies, and a lot more features are included in the Nautilus software. For example, if you've got a short weight of 20 grams, that means the part weights plus the runner weights are 20 grams, then we know that we cannot choose a very small machine, we cannot choose a very large machine, and we have to choose the right machine with the right tonnage, the right shot size, the right residence times. The mold has to fit in there. You have to have the right ejector stroke available on the molding machine. So there are a lot of features on the molding machine that we must consider before we select that machine. The Nautilus software will help you with this machine selection. Once you have the mold in the molding machine, now it is the responsibility of the processing personnel to develop a good, robust molding process. There are 11 plus 2 molding parameters on the machine that must be optimized in order to get a good optimized molding process. They are the cooling time, the pack and hold pressures, the pack and hold times, the melt temperatures, the injection pressure, the injection speed, the back pressure, the screw rotation speeds, the shot size, the transfer position, and the mold temperature. If the processor decides to split the pack and hold into two as pack pressure and hold pressure and pack time and hold time, then we end up with 2 additional parameters, and that's the reason we say it's 11 plus 2 molding parameters on the molding machine that will make a difference in the parts. There are also several outputs that we must always take into consideration, and it is these outputs that are more important compared to the settings on the molding machines. If you always match your outputs, you will get the same parts on every single machine that you mold the same part on. The goal should always be to achieve a robust process. The process should run in cruise control mode. That means once you put the mold in the machine, it should run without any tweaking, without any changes to the process, and still produces acceptable parts throughout the production run. Robustness is basically defined as having a process that is immune to all the natural variations. So I have developed a 2-step process for process development. The first one is called as the mold function qualification, also called as the scientific molding studies, where I not only find out an optimum setting, but I also find out the range of those optimum settings, because it is these ranges that I use to perform the DOEs in the DOE section to find out what is the exact setting where I can make good parts and if that process that I come up with is going to be robust or not. So the software provides all these worksheets. Back pressure is optimized by a back pressure study. Screw rotation speed is done with the help of a melt temperature study and a melt homogeneity study. Injection speed by the viscosity curve. Injection pressure by pressure drop study. The melt temperature by process windows and DOEs. Mold temperatures, process window and DOE. Pack pressure by process window and DOEs. Hold pressure by process window and DOEs. Pack time by gate-free study or a DOE. Holding time is by pack and hold studies. The cooling time is cosmetic limits, and a DOE. Shot size and transfer positions are usually set to about 95 to 98% fill in the injection phase. The software provides all these worksheets and a way to document this molding process. Once you have a molding process for a certain machine and you want to move that mold from one machine, let's say from a 100-ton hydraulic machine with a 45 millimeter screw, you want to move it to another machine which is 60-ton and a 35 millimeter screw, then instead of redoing the whole complete molding process, the software will provide you with the process sheet for the second machine with the click of a button based on the calculations that we have learned in the classrooms. There are lots of other features. As I go through the software, I will demonstrate these features to you. Over the years, the benefit that the software has produced has been enormous. For example, with this company that makes irrigation products, just in 1 year, they were able to save $100,000 on just one product. They use the Nautilus software, they optimize the injection molding cycle, they were able to drop the cycle time from 18.5 seconds to 12.5 seconds, and in doing so, the production units increased by 47% from 7.5 million to 11 million. This was a high volume part, and therefore they were actually going to go build a second mold, but because they were able to optimize the process, they did not need to build a second mold, and on top of that, they were able to reduce inspection on these parts. When they did the DOE and they adjusted the mold based on the results of the DOE, they found out that the dimensions could be very stable within specifications, and therefore they then decided that they did not need to measure the parts as frequently as they would, and so now they reduced inspection and saved not just time but a lot of money involved in the inspection process. And the return of investment, the software cost is literally the cost of one mold trial. So when I say one mold trial, that means if you calculate the cost of drying the plastic, putting the plastic inside the dryer, hanging the mold in the machine, taking the trials, cost of the material, cost of running the press, cost of program management, cost of inspecting the parts, if you take all the costs involved, it will easily be equal to one seat of the software. So if you are able to reduce one mold trial in your shop per year, that will pay the cost of the software. Having said that, let's now jump and look at the actual software. This is the home screen of the software. There are three databases. There's a material database, there's a mold database, and there's a machine database. All this data is input by the user. Then you come to the next tab, which is the compatibility tab. Select the mold that you want to use to run the compatibility report. Specify the tonnage for this material. Specify the percentage short size limits, and click on display compatibility. The software will now run a report where it will tell you which is the right machine that satisfies the requirements of the tonnage, the short sizes, the percentage short sizes, the residence time, the size of the mold, and any other rules that you may have put in there. It looks at all these rules and will now generate a report and tell you which is the right machine for the given mold. If you're doing this exercise to move an already established process from one machine to another machine, then in that case, you select the process sheet from the drop-down menu, and when you run the compatibility report, in the second tab, it will give you the process for any machine in the database. For example, this process was developed on machine 5. Now the software has gone ahead and calculated the process for every single machine in the shop. The machines that are in green shows that you can run this mold in this machine. And now let's say that you want to run it in this machine here. You come to the drop-down list, select the machine, click on go, and the software is now going to give you the process sheet for that machine. Even though you have never run that mold in that machine, I've already generated the process sheet for you for that machine. This is what is called as the process machine compatibility analysis. So mold machine compatibility analysis, process machine compatibility analysis, and the list of acceptable machines is where both these criteria are met. And so now you can actually select a machine where it's mold machine compatible and process machine compatible. So here is an example of how well the process transfer function works. One of my customers moved a mold from a 50-ton 30 millimeter screw machine to a 110-ton 45 millimeter screw machine. And when they looked at the dimensions, they measured two dimensions. They measured the post height and then they measured a post diameter. And the nominals were 3.25 inches and 2.807 inches. And you can see by using the process transfer function, the delta in the dimension between the two machines was less than a thousandth of an inch. In fact, in case of the post diameter, we almost hit the dimensions exactly the same on both these machines. So the process transfer function works very well. We have a lot of customers who have taken advantage of this and they don't have to redo the processes on the second machine. Then we come to the project. This is where we are going to go through all the worksheets for process development. You can either create a project or you open an existing project. So I'll open an existing project to show you an example here, the sample mold. And now you can see that all these icons are now active. You've got the melt preparation studies, under which you've got screw rotation speed study, where at different screw rotation speeds, you're going to find out what the actual melt temperature is and plot melt temperature as screw speed and pick your screw speeds from here. You've got a back pressure study. At different back pressures, you're going to mold 10 parts, weigh the parts and the runners, short shots, mind you, and you're going to generate a graph of the range versus back pressure and find out what is the optimum back pressure. You've got the 6-step study, which is basically the scientific molding studies. You've got a viscosity curve graphs, cavity balance, pressure drop studies, the cosmetic process window, the most important study of all, the gate seal study. There's also a gate seal study for splitting the pack and hold. There's also a gate seal study for a hot runner system based on DOEs. You can either use this worksheet or you can use the pack and hold study worksheet for hot runners also. And then you've got a cooling time study. These are the main studies that are involved with section 1 or stage 1 of the flowchart I showed you earlier. Once we have this information, then we go into the DOEs or design of experiments, and the software is extremely simple to use. You select your factors from a drop-down menu, step number 1. Step number 2, put in the highs and the low values that you get from the 6-step study. Step number 3, put in the tolerances for all the dimensions that you want to check, and you simply click on Worksheet. With 4 simple clicks, you already have the DOE generated. Mold these parts, put in all the dimensions for these experiments, and simply click on Analysis. Once you click on Analysis, you've got multiple tabs. From these tabs, you'll see it gives you the experimental information here. It gives you what's called as a tornado chart, which tells you the most important factors for that dimension, for that cavity. In this case, it's the holding pressure that makes the biggest effect. You've got a dimensional process window where you can plot contour plots based on the most important factors that the tornado chart tells you. In this case, it's a holding pressure versus melt temperature. The solid green line is the nominal value. So clicking anywhere on the solid green line is going to give you the process conditions to set such that you will get the dimensions at the nominal value. So in this case, setting the melt temperature at 501 degrees and a holding pressure of 900 psi with a cooling time of 11.5 seconds is going to give you the length of this part. For cavity 4, you're going to hit the nominal values on that dimension. The orange line here is the upper spec limit. This here is a lower spec limit. That means if I can now generate this window, this is what is called as the dimensional process window. That means if I maintain my temperatures between 485 and 542 and a holding pressure of 840 to 1058, I'll always mold parts to specifications within this window. And where would I set my process? Right in the center, out here. That would be 513 and 962 of holding pressure. This is what is called as a contour plot, and this is what is called as a dimensional process window. This way, the software has the ability to look at any dimension and analyze the data for all the dimensions that were put into the software after measurements. We also have the ability to overlay the plots. So if you have got two dimensions or two cavities, you can overlay the cavities and look at a composite window where both these dimensions will be in spec. For example, in this case, wherever the green lines are intersecting, you can say that these dimensions are going to be within specifications for both the cavities. We can also simulate the complete molding process. For example, the length of the part that you see here. This is cavity 4, cavity 5. This is the lower spec limit. This is the upper spec limit out here. And now it tells me that at a process of 510, a cooling time of 11.5 seconds and a holding pressure of 1000 psi, one can get the dimension of cavity 4 at 15.0589, cavity 5 at 15.0749, which is out of spec and therefore it's red. You can start playing with the process here. You can start increasing pressures and you can see how the dimensions changes here. You can start increasing melt temperatures and you can see how the dimensions change. At the same time, you can see what's happening to your parts over here. The advantage of doing these DOEs is also it can tell you very clearly which are the dimensions that cannot be brought into spec by process only. Because remember, this column that you see is the extent to which a dimension can be changed within a cosmetic process window. If I go out of this window, I'm going to have issues with flash or short shots, and therefore in this case, it's very clear, black and white, that you must change the steel on the mold or the product specifications, but nothing can be done with the molding process. So this dimension can never be in spec at the given condition of the mold and the process. But if you look at this dimension, this tells me that no matter what you do, you'll always be within specification. So in this case, you can actually reduce inspection. We can also give you the most optimum process. Let us say that you want to find out the process where most of these dimensions are going to be as close as possible to the nominal. You click on the gold spot button. You can select the cavities and the dimensions that you want to consider for these studies, and you click on OK. And then what the software is now going to do is it is going to calculate and tell you the most optimum conditions are 520 degrees Fahrenheit for melt temperature, cooling time of 15 seconds, and a holding pressure of 950 psi. And you can see here, this is at nominal and this is as close as possible to nominal. We did not consider this because out of spec, and this is always going to be in spec. So the software will also calculate the most optimum conditions for you. The other very useful tab is the suggested dimension changes tab. So if we go back to the process optimizer and we say that we want to run this mold at 520, 15 and 950 psi, then we can come in and say in the dimension changes, we say 550, 15 seconds and 950 psi. The software will tell us that we are about 19.5 thousandths away from the nominal. So now if we go change the steel by 19.5 thousandths, then we will hit nominal. So what the software also does is it helps you give you numbers, or it helps you make data-driven decisions to go change the steel inside the mold. So how well do the predictions work? So here's a good example. This is from one of my seminars. This is the July 2019 seminar that I taught. at my location. And every time I run my class, I do an actual and predicted from the software. And you can see here, this is the part that I use for the studies. This is the length of the part, the width of the part. And you can see from the confirmation run, you always have to do a confirmation run, and the actual numbers that we got from a sample size of 3, the actual numbers that you get is this column here, and the predicted from the software is this column here. And you can see that we are almost always predicting the dimension of the part very close to what it actually is. So the simulations that we have in the software, the algorithms that we have built in there, are very accurate, and they're going to get even better. And there's some more stuff that's coming in, which at some point I will give you some information about, but we have not released those modules yet. There are other tabs here. Please visit the website and download the PowerPoint presentation, and you'll be able to see the use of the other tabs. Plastic process sheet. This is where you record all the 11 plus 2 parameters. There's also quality data. In the quality data, you can do full dimension analysis. You can do statistical analysis, where you can find CPs and CPKs. You can do a post-mold shrinkage study. Under documentation, you can attach any external document to the software, or you can attach a link to a document from your server. Troubleshooting. This is a troubleshooting for the specific mold under consideration. If the parts from this mold have splay, what are the solutions? If the parts from this mold have got shorts, what are the solutions? So this is a mold specific troubleshooting guide. There's also equipment qualification worksheets, where you can do the 3 studies: injection speed linearity studies. You can do shot to shot repeatability study, and you can do a load sensitivity study. There are several calculators also available for the user. There's a learning center, where you can study about scientific molding, download the flow chart, download the 6-step studies. And under options, you can have users with user rights to modify or read certain worksheets. You can manage units between metric, English, and custom units. You can select where you want to save the database. You can import databases from an Excel worksheet, and you can upload your own company logo. So in all the printouts of all the reports, you'll be able to see the company logo on there. That was a brief introduction about the software. I hope you enjoyed the presentation. Please visit www.fimmtech.com and download a detailed PowerPoint presentation of the complete software. Thank you for your time.